So in today's lecture, we are going to start to study about Lie groups. Now, to give you a quick motivation of why we are studying a Lie group, I'm going to take 10 minutes of time. So the motivation is the following. So symmetry is very important in physics. Okay, we all know this. Symmetry in a particular theory you might have seen first time in electromagnetism. So let me remind you about the gauge symmetry that you have encountered in electromagnetism. Okay, so this is the first time you might have encountered the symmetry. So what is gauge symmetry? Let me remind you that if you have your vector potential and you have your scalar potential, and if you change them to some new vector potential and scalar potential in a certain way, so the change has to happen in a certain way, then you will see that the whole Maxwell equation remain invariant. Okay, so this is a symmetry. So symmetry means you do something with the object which makes the theory, and upon doing something you see that the whole theory doesn't change. So that is symmetry. So you might have seen gauge symmetry in your textbooks, and it's quite common. Next, what we want to understand here is, so we have this gauge symmetry, all right, but we know that we have some other theories. For example, our world, as of now, we know that our world has strong interaction or strong forces. Let's write them in terms of forces. These are the four fundamental forces that we have encountered till now. So strong force, then we have a weak force that causes decay, so I'm not writing force. Then we have electromagnetism, I'm writing it as EM, and then we have gravity. So these are four fundamental forces about whom you have been studying since long. Now there was something very interesting about these fundamental forces. It was seen that any theory that gave birth to strong, weak, or electromagnetism, they all were described by a theory that had gauge symmetry. Just like the Maxwell equations, they teach you what electromagnetism is, and Maxwell equations are invariant under gauge transformations. So we say that there is a gauge symmetry in Maxwell equations. Similarly, there are symmetries in strong, weak, and electromagnetism, and the symmetries are all gauge type symmetries. So all this, so these three forces, so we have this strong, weak, and electromagnetic. These three forces are described by theories that has gauge symmetry, and not just any gauge symmetry, a special kind of gauge symmetry. So let me write. So special kind of gauge symmetry, and it has a name, and we say that this is described by a kind of gauge theory which is called as Yang-Mills theory. I know I'm not writing any hardcore Lagrangian here, so I'm just giving you an overview and a motivation that will lead us to Lie groups. So strong force, weak, and electromagnetism are described by a kind of theory, and that theory is Yang-Mills theory. Okay, so it is special in its own right. But this gravity Well, gravity also has this gauge symmetry in it, no doubt, but it is not of Yang-Mills type. And we have a different theory that describes gravity, which is the general theory of relativity. It has nothing to do with Yang-Mills theory that describes strong, weak, and electromagnetic force. So we know that general theory of relativity is more geometrical in nature. Relativity, VITY. Now, the next question that we need to ask ourselves is, okay, let me give you what is Yang-Mills theory. Well, one way to understand what is Yang-Mills theory is that it is just a generalization of Maxwell equations. You can think in that way. Okay, and you see that Yang-Mills theory describes the three forces, and gravity is described by a different kind of gauge theory, which is a general theory of relativity. It is different, and it is the odd man out for what we know till now, and thus the symmetries that are there in this theory, especially I'm talking about strong, weak, and electromagnetic theory. Using this, we all know that we have this standard model, the one that you will read in usual textbook, and that in the textbook you will see this phrase to be written, that our universe, and you will see this weird looking thing, SU3 cross SU2 cross U1. So in this lecture, first of all, you will understand what is the meaning of this SU3, SU2, and U1. So you will have a confidence that, okay, once you understand these terms separately, and then you will understand what does it mean when you have all these three terms multiplied to each other. So as already described in one of the previous lectures, that when you write the Lagrangian for quantum electrodynamics, we see that it is invariant under U1. We discussed that in short, and we will do this in more detail later on. Well, some more interesting information is that the strong interaction and the theory that we study for strong interaction nowadays is called as QCD, quantum chromodynamics, and the gauge group for this theory, so the gauge group, so every symmetry, so when I say gauge transformation, gauge symmetry, now every symmetry means I'm talking about some group. Okay, so a group is a collection of elements, and all those elements are operators. Okay, so and they create this symmetry, but the gauge group is SU3, and we all know that the weak interaction and electromagnetic force, they were these two forces were unified. So we are nowadays in physics, we are talking about unification. So the strong, weak, electromagnetic, and gravity, everything should be unified to one thing, and that one equation that describes our world. So we are working towards that. So the first unification happened with weak interaction and electromagnetism, and the unified theory of weak interaction and electromagnetism is called electroweak theory. Electroweak theory. Now the gauge group for electroweak theory, so the gauge group for electroweak theory is SU2 cross U1. So I don't have to talk about weak interactions and electromagnetism separately. I'm talking about both of them in a unified manner. So the idea is, can we unify all these forces? And gravity is creating a big issue because it is completely different. So the theory that describes gravity is very much different from the theory that describes strong, weak, and electromagnetism. And that's the whole idea about quantum gravity. So the idea of quantum gravity is somehow can we quantize gravity, and then we can join this quantized gravity with other quantized, like we know that when I talked about strong interaction, We learn quantum chromodynamics. That means the strong interaction in its quantized version. When we talk about electromagnetism, we talk about QED, quantum electrodynamics. So given the electrodynamics thing was quantized, and Feynman and other people did a lot of work. Similarly, then Weinberg and many other people, they unified this electromagnetism and weak theory, and they got this electroweak theory. But now the whole idea is, can we unify all these four forces? And string theory seems an candidate that says that, hey, my theory has a gravity inside it in a quantized manner. So, but we will not focus on that. So this is a clear picture of what in physics we are doing and what we have. So the strong, weak, electromagnetism, all these three, they include the standard model that we talk about, the standard model of particle physics. But now you understand that whenever we talk about the standard model of particle physics, we talk about symmetries. When we talk about symmetries, we talk about groups and the kind of groups, SU2, SU3, U1, etc. So our main target in this lecture series will be to understand these terms, and these are all part of Lie groups, and that's why I said the name of our chapter is Lie group. So this SU3, SU2, U1, they all belong to this special name called as Lie group. Okay, that's it. So that's the initial motivation of why we are going to understand Lie groups, because when we understand Lie group, we can understand the whole idea of standard model. So what I'm going to do now is, now I'm going to jump to a quick review, and this review is going to be very interesting with some new examples. So since we are starting this lecture after some break, so I thought of giving a review, but in an interesting manner. So let me start the review. So we know that we were talking about group theory, and by group theory I was talking about a set which contains some elements, so elements like A, B, C, an identity element, and dot 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 dot. So this group can be finite or infinite depending upon what kind of group you are choosing. Mainly previously we talked about finite groups, where we have finite number of elements in this set. So group is a set, and this set of elements, they behave in a particular way. For example, we know that if we multiply any two elements, I may reach a third element somewhere in the group, and also they contain their inverses. So A must have A inverse, which is also contained in the group, and it can be element F, A, B, C, D, E, F, dot 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 dot. B can have an inverse of its own, and it can be some element G here, and so on. Now, and then we read about representation of group. So when we talked about representation of a group, I said that each group element, so each G, and G belongs to capital G, so each G is represented by a matrix. So this was the whole idea of group representation. So it is represented by some matrix, and these matrix that represent this group should follow the same same properties that this follows. So each element is represented by a matrix, and hence when we talk about representation, we actually talk about matrix representation of G. So we don't do the matrix representation of a set, but we do the matrix representation of set elements. So A, B, C, they will all have a matrix representation. Well, what kind of matrix? Well, the matrix can be anything. As I said, we can use 2 cross 2 matrix. We can use 3 cross 3 matrices, and so on. The matrices that we use, they can be orthogonal matrices. they can be unitary, etc. So let me come to make you understand. So consider there is element A that belongs to group G, and there is element B that belongs to group G, and when A and B multiply, that give me C, which also belongs to group G. Then under matrix representation, so if I have a matrix representation which is orthogonal, so by that I mean the matrices that corresponds to the group elements are orthogonal by nature. What do I mean by that? So consider I have an orthogonal matrix that represents, or that is a matrix representation of A. I have an orthogonal matrix that is that is the matrix representation of B. Then if I multiply these two representations, the matrices of these two elements that represents the element, I'll get the matrix representation of C. And why I'm writing O is because all these matrices have a property, and that's why they are called orthogonal. So take any matrix that represents the group element, and if you write the transpose of the matrix and multiply with itself, you'll get identity. So if this is satisfied by the matrices that represent the group element, we call that we have a orthogonal matrix, and this orthogonal matrix is representing my group elements. But again, this orthogonal matrix can be 2 cross 2, 3 cross 3, dot 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 dot. Okay, you can go to higher dimension representations also. I will come to an example for more understanding, so no need to worry. So you can have a unitary representation. For example, instead of using A, so consider these matrices are 2 cross 2. For example, you found that you can have 3 cross 3 matrices that represent the group elements of G, and interestingly in 3 cross 3 all these matrices are denoted in this way. Now why I'm writing U? Because of course this is a 3 cross 3 matrix that is different from the previous matrix, and the reason I'm writing U is because all the matrices that represents the group element, all these matrices they satisfy a special property, that is, take any matrix and do the dagger, multiply with U itself, you get identity. We know what dagger is, right? So it is like a transpose and conjugate, and in the orthogonal part we just took transpose, no conjugate. So for example, the matrix that represents A, so if you take this, put this dagger here, and then you multiply with this, you get 1. Sorry, the identity matrix. So that is matrix representation of group elements. Well, it can be reversed. Maybe sometimes you have a group and the 2 cross 2 matrix is unitary, and maybe the 3 cross 3 matrix is orthogonal, or you can have 2 cross 2 matrix representation which is unitary, and you can also have 3 cross 3 matrix which is also a unitary. The story doesn't end here, because then further we studied about these matrices, and what we studied is that we can have other equivalent representation of the same group elements. So other equivalent representations of group elements G. So what do you mean by this equivalent representation? Well, you will see a very interesting thing here is that if I have, consider U of A is a matrix representation of element A of the group, then I can find another matrix U prime of A. This is a completely different matrix, but it is also unitary, and I found it by multiplying some matrix V with the old matrix UA that represents elements that represents the element A, and V inverse here. Now what is V? V is some matrix. Okay, how do I find V? How do I choose V? We'll come to that later on. So V is some matrix, and under this matrix you get new matrices. So similarly, if I have this old representation of element B, then again by applying this V object in this particular way, I get a new matrix representation of element B. Okay, now all this we will do an example. Explicitly we'll see examples. So keep that in mind. If you don't understand, no problem. Just keep that in mind. So now let us see if I do this kind of thing, then things are satisfied or not. For example, remember we had here that if I multiply element A and B, I used to get C. That means in a matrix representation, if I multiply the matrix representation of A and the matrix representation of B, I should get the unitary matrix representation of C here. So the question is, can this thing, can the new matrices here, they satisfy? Let's try to understand. So let's try to multiply U prime A and U prime B, and let's see if it satisfies the group axioms. So U prime A is V UA V inverse, and U prime B is V U of B and V inverse. Now you need to look at it. You see that you get V and V inverse here, and they go to identity. So that's very nice. And then what do I have at hand? I see that I get V U of A, the old one, U of B, the old one, and V inverse. And then we know what this is. It is V U of C and V inverse. Now you would say that what did we get? Well, we found that if this object represents A and this object or this matrix represents B, then we knew that C should be represented by this kind of object. This was our intuition. We knew that C should be represented by this kind of object, and we saw that it is the case, because we know that when you multiply A and B, you should get C, and you got your C, and it looks the way we want it. So this is equivalent representation. So you have one representation, and from there you can go to some other representation. We'll come to a very concrete example. What equivalent representation can do? What it can do is it can reduce your representation. So the idea of reduction comes from the existence of equivalent representation. So reducible representation, will come to that. But before that, before this understanding of reducible representations, I would like to give you a quick example for whatever we did till now. I'm going to give you a very quick example. So the example goes like this, and it's very simple. So okay, let's do it in the next part of the page. So the example goes like this. So consider you have a group, and the name of the group is D3, which is a symmetry group of equilateral triangle. We already discussed this in our last lecture, and I'm going to use some new notations here. So consider the elements are identity A, B, C, D, and E. So these are the elements of the element D3. Okay. Now what are the group operations? We found that when A multiplies with A, you get B, and when C multiplies with B, you get element E. When B multiplies with A, you get identity. When D multiplies with A, you get E, and so on. You can make a table out of it. And if you search about this symmetry of equilateral triangle as a group, which is the D3, you can find what element multiplies with what element gives you what element, but all those multiplication will give you elements that lies inside this group. You will not get anything that is outside the group. Well, now what to do? Well, now the first thing I can show you is we do have a 2 cross 2 representation and 2 cross 2 unitary representation of all these elements. So first thing I'm going to show you is that there exist 2 cross 2 matrices. Especially I can write 2 cross 2 unitary matrices that represent these elements. Okay, so let me give you some examples. We know that identity is always represented as 1 0 0 1. Okay, and then you will find that u of a has a very interesting representation, and it looks like this. So you have minus half here, and you have root 3 by 2 here, and then minus root 3 by 2, and then minus half. So this is the matrix representation of A. Similarly, let me write it for B. I'm not going to write for all the elements, just for some of them. So for B, you have minus half, you have minus root 3 by 2, you have root 3 by 2, and you have minus half here again. Please check if these are correct or not. You can search it from the internet, and you see turns out to be 1 0 0 minus 1, and so on. So you can write 2 cross 2 matrices for all of them, all these 1 2 3 4 5 6 elements. So I just wrote it for 4 of them. So what is the interesting thing? We know that when A multiplies with B, you get identity. That means if you take the matrix U of A and you multiply with the matrix U of B, you should get the identity matrix, which is nothing but U of 1 or U of I. Okay, we know that A and A gave me B. That implies if you have the matrix representation of A and you multiply with the matrix representation of A again, and you get the matrix representation of B. So the whole thing that the group elements behave, the whole behavior is mimicked by these matrices. Similarly, we know that C and A can give us D. That means if you take UC and multiplied with UA, you are going to get UA, then you are going to get UD. So you can check this thing. You can just multiply the matrices and you'll see that all these properties that the group element satisfy, the matrix also satisfies. Well, I told you about 2 cross 2 unitary matrix representation of this above group, which is the D3 group. But I also said we can have some other representation in some other dimensions. So now for the same group, I'm going to give you for the same group T, I'm going to give you a 3 cross 3, again unitary. So it's quite interesting. We get unitary in 2 cross 2 and we get unitary cross 3. So unitary representation, and this representation is not only 3 cross 3 unitary, but this is also reducible representation. And I'll come to this idea of why it is called as reducible representation. But let us first write the matrices that represents the group element. Well, the identity element in 3 cross 3 is nothing but 1 0 0 0 1 0 0 0 1, and the matrix representation of the element A turns out to be 0 1 0 0 0 1 and 1 0 0. Similarly, let me write it for B also. Let me do it first. This, and this, and so on. So we have 6 matrices that mimic the same thing. For example, now you have what? You have A and A, when multiplied you get B. Similarly, in 3 cross 3 representation, if you have UA and multiply with UA, you should get UB. make sure you check them if there is any error with the numbers, but this should hold. Okay, so the whole thing is made. Well, I told you about representations, but what about reducible? Why I use the name that this is the representation that is reducible? I didn't write it for 2 cross 2, but I wrote it for 3 cross 3. Why it is not only the unitary 3 cross 3 representation, but it is reducible? Well, reducible representation means, so consider U of A is the representation of the group elements. By reducible, it means you should find some V. Remember what V is? It gives us new matrix. So V will give you a new matrix that represents A. And how does it give you? It says that, hey, write U of A, multiply V inverse here and multiply V here, and it gives you a new matrix. And the special thing about this new matrix, it is a block diagonal. By block diagonal, it means some elements are here, some elements are here, and rest all the elements here are 0. This is the idea of block diagonal. So this is non-zero, this is non-zero, everything else is 0. So then we say that the matrix representation is reducible. Now let me give you a quick example. Well, the V actually exists for the above 3 cross 2 matrix and looks a bit complicated. I'm going to write it and you're going to do the calculation in your home and correct that these numbers are correct. So this is 3, 1 by 3, then I have 1 by root over of 6 here, minus root over of 2 by 3 here, and 1 by root over of 6. And I have 1 by root over of 2, and I have 0, and I have minus 1 by root 2. Well, so V exists. That's the beautiful thing. Now what happens when V exists? When V exists, take any. So G is any element that belongs to group G. So G can be A, B, C, D, E, I, anything. Multiply V here, multiply V inverse here, and get the new matrix set for any element of G. So let's get our new matrices. So the identity won't change. So this is again the same. 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. And then we have this new matrix for element A, and look at how does it look. I have 1, 0, 0 here, and I have a 0 here. I have minus half here. I have root 3 by 2 here. I have a 0 here. I have minus root 3 by 2 here, and I have minus half here. And this will remind you something, and I'm going to tell you what it's going to remind you. Well, if you look at this carefully, this is block diagonal. If I can do this thing. So hence it's a block diagonal. So it is a new matrix, and it is block diagonal, and that's why we say that the 3 cross 3 representation of the D3 group is reducible, because you can find a V that gives new matrices which are in block diagonal form. Well, let me remind you, what is this? Let us look at what is this. Minus half, root 3 by 2, minus root 3 by 2, and minus half. Where did we see this thing? So let us look at U of A here. We have this minus half, root 3 by 2, minus root 3 by 2, and minus half here. So this is U of A, which is the 2 cross 2 representation. So the 3 cross 3 representation turns out to be identity 0, 0, 0, and here we have the 2 cross 2 representation of A. So let me write 2 cross 2. That's very interesting, right? So that means the 3 cross 3 matrix turns out by equivalent transformation that it is composed of one-dimensional representation and a two-dimensional representation of the group element. Well, let me remind you, when I say dimension, think about basis. Every representation is built upon basis. The 3x3 representation is built upon a vector space whose basis set has 3 elements. That's why we have a 3x3 matrix. The 2x2 matrix is built upon a vector space whose basis has 2 elements. Hence, we have 2x2 matrix. And what do you see here is that if you have a 3x3 matrix representation of group element, that means you have a vector space whose dimension is 3. And it is reducible representation because you get block diagonal, and in the block diagonal, what do you get? The first element in the block diagonal is nothing but one-dimensional representation of the group element, and the second element in the block diagonal is a 2x2 matrix, which is a two-dimensional representation of the group element. By two-dimensional representation, I mean representations are actually matrices which are 2x2, and 2x2 matrices are built upon the vector space that has 2 basis elements. I discussed this in great detail in our previous lecture. Okay, so I think I have given quite a good review of what group theory we did before with some new examples at hand. So this will add to your note. Now, this is the end of what I had to say for today, and the whole idea is now that we are going to read about continuous group, and this continuous group is something that will take us to the idea of Lie groups. So this we will do in the next lecture. I hope this first lecture was a quick reminder of the whole idea behind group theory, and then we will continue our lecture with the Lie group, and I will try to finish it as fast as possible so that we can move to differential geometry. If you have any doubt.
Sir. Yeah. Okay. So you said that we have 4 forces, right, in our universe, and among these 4 forces, these 3 forces like this, strong, weak, and electromagnetic, they have some kind of group, right? I mean, they are associated with some group, and for gravity also we have some group, right? Because they also have some gauge symmetry. But can you say that what kind of group they have? I mean, in case of gravity, like in case of strong force, we have SU3, like that.
The whole idea of group actually belongs to when you can write a quantum field theory type of thing for these forces. So when you build a theory based upon the idea of quantum field theory, and we were recently discussing that how Feynman tried to write gravity in terms of a field theory model, right? So
yes.
The whole idea is that can you write a quantum field theory type of Lagrangian that can give birth to gravity, and the work is going on now. General theory of relativity is a gauge symmetry, and the group I have to search. I don't know. I have to search.
Okay.
But I don't think there is the notion of group here. The reason is we always associate group with the Lagrangians, right? We say that it is invariant under such and such transformations. But for gravity, we don't have that kind of field theory Lagrangian for which we can say that, hey, look, we have this field theory model and these are the gauge symmetry. Well, in gravity, the gauge symmetries are actually coordinate transformations. And, and there are some issues. There are some issues with gravity, and maybe after finishing group theory lecture, we will have this discussion.